Hi everyone and welcome back to the multiverse of 100 plus data science project series. In this video, we will discuss about the autism spectrum disorder predictions using Python and machine learning. So in order to doing the autism spectrum disorder classifications, we're going to be using here dataset from the Kaggle. This is a dataset. In this dataset, it have the two file train.csv, test.csv. Just go on the Kaggle and sign up with your account and download the dataset from here. First of all, you're going to importing here the important library. And after that, you're going to building here our machine learning model, as well as you're going to do our data preprocessing. So first, I'm going to importing here NumPy. So let's say import NumPy as NP. Then I'm going to import here the pandas as PD. Then I'm going to import here the matplotlib. Let's say import the matplotlib dot pyplot as plt. Then I'm going to import here the cborn as SNS. So after 9 days later on, actually making the videos regarding the data science project, so that's why quite problem in the typing. Keyboard is also stuck. That's why. So then I'm going to importing here from sklearn.preprocessing. Import here the label encoder. Now let's say from sklearn dot pre-processing. So you can also use the tab key from your keyboard and it will give you the auto suggestions, and make sure that your internet connection is on so that it will give you auto suggestion quickly, but it not give it yet. So let's say pre-processing. Yep, right now you can see pre-processing, and I'm going to import here the label encoder. Let's say label encoder. So label encoder actually help us to encode your categorical value to the numerical one. And after that, from sklearn sklearn dot model selection. So we're going to import here the train, test, and split, so that we can divide our data set into training and testing part. So let's say train, test, and split. And then we have the cross validation scores, so that you can also checking here the cross validation scores. And then I'm going to importing here the randomized CB. So randomized CB is nothing but used for in the case of hyperparameter tuning, so that you can also do the hyperparameter tuning in some kind of algorithm, just like the random forest or decision tree or XGBoost. And after that, I'm going to import here another library called the imbalance. So I need to import it from, let's say imbalance. So imbalance dot oversampling, then oversampling. Then here I'm going to import here the SMOTE. Now the question is, why this library, why this imbalance, and why the oversampling? Because the data set that you're going to using it here, it having some data balance issue. So in order to removing this issue, you need to do the oversampling. Okay. So you can also do the undersampling, but when you do the undersampling, your data should minimize. So it is a best practice. If you have the minimum number of data, you can use the oversampling. No problem. When you go to this part, then you discuss about that. Why should you use the SMOTE? Okay. And after that, we're simply going to import here some of the machine learning algorithm, just like the decision tree classifier, random forest classifier, and the XGB classifier, because we're going to do the hyperparameter tuning. So let's say sklearn dot tree. We're going to import here the decision tree classifier. So you can also making it by own. I am already making some videos regarding that. How can you creating your own machine learning algorithms from scratch? So you can also using here your own decision tree classifier. Otherwise, you can also use it from the scikit-learn. Now let's say from sklearn dot ensemble, because it's nothing but in the case of ensemble, we are going to importing here the random forest. So random forest is nothing but one ensemble technique, just because of it will just taking so many of the decision tree, and it will taking the result from each of the decision tree and combine them and getting the best result. That's what it's called, the ensemble. Now from XGBoost, so I'm going to importing here the XGB classifier. It should be the XGB classifier, because this is an classification tab. If the person or uh, if the child has the child facing the autism or not. Then from sklearn dot metrics, so we're going to import here the accuracy metrics. I mean accuracy score, then the confusion matrix, and as well as the classification repeat. Okay, and then you're going to import here the pkl so that you can also save the data in the form of pkl format. You can dump it. Now we can simply go into loading our data sets. So let's say pd.read_csv. So you have the two data set in the form of csv. One is a train.csv that you see in the Kaggle, and another one is test.csv. So you're going to using here this train.csv and make sure that you receive the file inside the same directory where you created here your notebook. So this is the df. Now you can see the df.head, and you can see here this is the data set, how it look like. So you can check here the shape of the data set, how many column and row it have. So it have the 800 row and 22 columns. So 22 columns, it also have one target column, which is nothing but called class ASD. It's nothing but the autism spectrum disorder. If the person, if the child have or the person have, so you need to classify them. So that's why I actually imported here this decision tree classifier, random forest classifier, and the exhibit classifier. Cool. Now we can simply go checking the tail of that as well. So let's say df.tail. So if I enter it, you can see here that it has the last some column and the row you can see, that you can see on here. So the first five, and this is nothing but the last five. So you can also give it here 10, 20, whatever you can give it to here. Now we're simply going to add here our all of the columns of the data frame so that you can display it. There's a pd dot set option. You can setting here one option so that you can display the maximum column, because this is an long data sets. So let's say max columns, and then you can give it to here the nan. So if I see the data.head, you can see the same thing. So you can see the same thing. Okay, same thing. But if I see here, you can see the same thing. Okay, but it will just setting here the maximum value of that. Okay, that's not a very. Now you can checking here the info of the data. I mean, you can checking here the column name, if there any missing value or not, also the data type. And if I see that it have the 22 columns, total 22 columns, and starting from id and ended at the class asd, it have the two floating point number and 12 integers and 8 is objects, I mean the categorical columns, and 12 is numerical column at well. Now we can simply go into checking the type of that. And if I check here the type of the age is nothing but the float third 64. And if I checking here the age, so age is nothing but a point 38.17 like that in the data set. So each cannot be an floating point number. We need to also convert them into integer format. It's called the typecasting. Okay. So we can using here df of age is equal to df of age, and you can simply go into make it in the case of integers. Okay. So if I check in the now df.info, then you can see the data frame is converted into the int 32. Okay, you can also make it int 64, whatever else, but data type is integer 32 bit. Okay, so cool. Now we can simply go into checking the head of that. So let's say df.head. Then you can see here the floating point number is getting converted into the integer from 38 years old, 47 years old, 7 years old, 23 years old, like that. So in the case of data frame, it have the floating point number. This is also called the data preprocessing. Also, you need to look about your data, how your data look like, is there any misinformations or imbalance or not. Okay, so now we can simply go into checking here uh, all of the values from here. Okay, so what I can do is simply going to checking all of the columns from here. So let's say for call in df.columns. So in here, what I can do is simply taking here the numerical columns. So numerical column is nothing but the ID, the ages, and the result. Okay, result can be also the numerical. You can see result is also be numerical. So what I can do is simply going to making all of the things I mean checking that how many unique value it have. Because if I check in the id is nothing but 800. 800 is the unique id. And if I see the age, it also have the so many unique value. And in the case of result, it's also have the so many types of unique value. Okay, that's mean I need to checking here the lowest number of unique value from here. So now what I can do, we have some reserved column or reserved features. So let's make it as a numerical features. I hope so you understand that. I mean, you checking that each of the column how many unique value it have, so that you can also do the encoding. Because id is unique, so it have the 800 unique value. Same thing for the ages and same thing for the results. But all of the cases, in all of the cases, it's not the it don't have any value greater than 5 or 10s. Okay, so we can checking this out. So we can taking it here. So accept the id, the age. So we have the age, and as well as the result. Okay, so accept the id, age, and the result. We're simply going to taking it. Let's say for call not in numerical columns features, we're simply going to printing it out. Let's say print here. We're simply printing here the columns and df of columns dot unique. So let's say unique. Okay, I mean checking for the unique value of that. That's it. So you can printing it out. So let's say printing this out. I can simply going to using, let's say 20. Okay, that's the mistake. I have to using here this one. So you can see that in the case of a1, a2, it have the two unique value, 0 and 1. In the same case of gender, female and the male. And in the case of ethnicity, it also have one question mark, so you can replace them with the others. And also jaundice, no, yes. Autism, no, yes. Country of resistance or state, you can say. So it also having some problem in the case of Vietnam. You can see also have the space. You need to replace them. And also it have the American Samoa. It can be the United States, as well as it have the Hong Kong, right? So it have the Hong Kong. So Hong Kong right now is under the China, so you need to also convert them the Hong Kong in the case of China, because it's right now in the country of the China. Okay, so you can say Hong Kong. And used before, yes, no, and relative, self relative parents and others, so we don't need it at all. We also replace them. So now what I can do is simply going to first replacing here this ethnicity, but before that we can removing here this age description, because it's not need at all because we have the ages. So we can simply dropping this out. So let's say df equal to df dot drop, and you can simply going to give it to here the columns. And inside this columns, you can simply going to give it here the id and the age description. Okay, that's a dsc. That's it. Okay, we can dropping this out, and now we can check the shape. So before we have the shape is nothing but the 22, now it's 20. Cool. So now we can simply go into checking here the resistance, the country one, so that you can replace them. So let's checking this one country one first, and after that you're going to replacing here this antiquity. Okay, ethnicity, I don't know how actually spelling. So what I can do, you can do copying here this one, ethnicity like that. I don't know how it pronounce. Okay, so let's say df of country of res, and you can simply going to using here this unique. So you can checking here the unique value of that. So any problem? Okay, I'm not using here this one just. So you can see the values. Now you can simply go into removing here, I mean replacing here this Vietnam, and remove the spaces, and America, uh, the America Samoa should be the United States, and the Hong Kong should be in the China. Okay, so you can creating here a mapping. So we can replacing them. Let's say Vietnam. So it should be Vietnam. replacing should be the Vietnam, and then America, American Samoa to the United States. Let's see, United States. So you can copy it from here, and then we can simply go into replacing here the Hong Kong as well. So it should be the Hong Kong. So Hong Kong should be replacing with China. That's it. Okay. So let's take a more shell. And after that, you're going to be replacing them. So let's say df of country, uh, country of resistance, this ones, and then you can simply go to using here this one, and then you can replace it. Let's say replace with mapping. So I hope so. To replacing, we can simply go into checking here the unique value of that. This is called the data preprocessing, right? So you can see now you don't have any Vietnam. Yep, Vietnam is replacing as well, and you don't have any America, Samoa, and as well as the Hong Kong. It converted into the China. Okay, so now we can simply going to checking here the class ASD. So we can checking here how many unique value or value count it have. So it's a class ASD dot value counts. So you already know that it is an imbalanced data set that you can see. It have the zero is nothing but 639, which is quite high. It's just like the 70-30 like that. So the class is imbalanced. Okay, that one portion you can got on here. Now what I can do is simply checking the description of the data set. This is a df.describe. So you can see here count, mean, standard deviations, the minimum, 25% percentiles, 50% percentile, and the 75% percentile. Okay, that you can see minimum value is 0. So most of the value is nothing but 0 and the 1 because it just have in the some kind of categorical column. So let's try to do some data visualizations. So what I can do, I'm going to setting here one grid theme. So let's say set theme is equal to, let's say style is equal to target, and then we can simply going to creating here an histogram plot for the age. So it also converting here this one because it has have the question mark. Okay, replace this later on. First let's try to do some hist plot. Okay, so we can using here sns dot hist plot, and you can simply passing here df of age, and then you can give it here this kde should be the true, and you can give it here plt dot title. So it should be the distribution of the age. Let's say distribution of the age, distribution of age. And after that we need to checking here that is there any outlier or not, because you already checked that it also have the data imbalance problem. Okay, so now we can checking that is there any outlier problem or not in the case of age or in the case of others columns. So what I can do, we taking here the age mean. So let's say age mean, and let's say df of first age and the mean, and age median, df of age dot median. First you're going to creating here an xb line so that you can see that mean and the median value of the ages, and after that you're going to checking for the outlier so that you can remove it based on the I keyword intel quantile range. So you can simply going to print it. Let's say print here the age mean. And then we can simply going to use it here the age mean, and you can simply printing it here the age median. Let's say age median, and then you can using here age median, And after that, you're going to creating here an xb line. So let's say plt dot xb line in a vertical, so that you can see the mean and the median value of that. And you can also classify them, is there any outlier or not. And otherwise you're going to plotting here on box plot in order to showing here the outlier. So let's say line style. So line style, let's give it here the dash dash dash. Let's say line style is equal to dash dash dash, and then you're going to give it to the label. So label is nothing but the mean. So you can copy it from here and you can pass it to here. So this is the median, and in the case of mean, you're going to give it here the median, median, right? So xb line plt.legends. Now you can using here this plt.legend and plt.show. Now you can see here the mean is nothing but the 27 and median is nothing but the 24. Okay, so that's mean most of the values nothing but the 24. We can say that, and the range is between this 20 to 27. 24 to 27 is nothing but the range of that, and most of the values is lies between the 60 to 80. You can consider this one as an outlier, but not at all. But most of the value is lies between these 24 to 27s. Okay, like that. Okay, so we can also do the histogram plot of the result, because if I see the result is also nothing but one the numerical columns. So you can also do the hist plot of that. So you can copying this out, and instead of doing the h mean, we can simply going to make it as a result. So let's say result, and this is the distribution of the result, and then after that you're going to use it the h mean to the result mean. Let's say result mean, and then here you go, it should be the result as well, and here you go, it should be the result as well, and then it should be the result. We can copy this out because otherwise it's taking time. Okay, and it should be the result. Okay, and it should be the result. So result mean, we can copy it from here, and hope so all is correct. Now in the case of result, the mean is 8 and median is 9. That's mean the in the case of result, all the values is lies between, most of the values lies between the 8 to 9. Okay, I mean the mean and the median value of that. Now you can checking here the outlier of that. Okay, because we checking that most of the values between lies between the 24 to 27. So you can now checking for the outlier. Okay, how many outlier it have, so that you can also removing them. So let's say sns dot box plot. So you can using the box plot, and you can simply going to using here x is equal to df of age, and then you can using here plt dot title, and as well as you can passing here box plot for each. Okay, you can say like that, and then you can use here an x level. So x level for the each, plt dot show. So in the case of mean and the median, we see that some value is going to the consider as outlier. Same thing in here, you can see after 60 it will considering all the values as outlier in the case of ages that you can see on here. Okay, that you can see on here. Cool, that's also one good point. You can remove it. So you can also checking the outlier in the case of result as well, because result is also a numerical value. So you can just plotting here uh, the outlier in the case of numerical values. So let's say result. So this is nothing but for the result, and this is the result. So in the case of result, it don't have an outlier, it's just having some minus point. This is considering as the outlier, so not so at all. But in the case of age, it have so many of outlier. Now how can you removing this outlier? So you can removing this outlier using a formula called the I keyword, also called the interquartile race. And using this formula, we can simply going to remove it. So in the case of I keyword, it has the lower bound and the upper bound. So you need to calculating this out. So if I write in the formula of the I keyword, I keyword formula is nothing but called the Q3 minus Q1. Should be capital. Okay, Q3 minus Q1. And if I calculate the lower bound, the formula is q1 minus 1.5 into I keyword. Okay, in the case of upper bound, the formula is considering as q3 min plus 1.5 into I keyword, like that. This is the formula for the I keyword. So here you can removing here the outlier in the form of lower bound and upper bound. If you see here, it have the lower bound value as well as it have the upper bound value. Okay, so you can using here this formula. So let's taking it out. Let's removing here the uh, outlier in the case of ages. So how can you calculate the q1? So q1 is nothing but called the 25% percentile. So if I'm simply going to using here df.describe, that you can see it have the 25% percentile, 50% percentile, and 75% percentile. You can just go on the Google and search for that, what is the curve. And in the case of curve, so if just assume that in the case of this curve, this is called the 25% percentile, this is called the 50% percentile, and rest of them is called the 75% percentile. And if I calculate the IQR, you can calculate the IQR from like that. So you can go on the Google and search for the what is the IQR, how can you calculate them. You can get one graph like that. So I'm not going to wasting the time on here. So that's a df of age. So you can say the age, and then we can using the quantile. So let's say quantile. And in the case of quantile, we're simply going to give it to here the 20%, 25%. And in the case of q3, so we have the df of age, and we can using here this quantile of 0.75. Okay, now you can simply going to calculate the age outlier. So what you can do, you can calculate them. Let's say age outliers is equal to, so you can calculate it from the df. So df, and in the case of df of the age, so if it is lower than the lower bound value, so let's say lower bound, and or df of age greater than upper bound, so let's say upper bound, and this is considering as the outliers. So if I check in the age outliers, so those are the value which can have the outlier. Okay, so you can also checking here the length of the age outlier. So outlier, so you can see it have the 39 outlier. You can also printing here this lower bound. So I can taking it here, let's say lower bound, you can printing it here, let's say lower bound, and you can say the lower bound. Okay, and in the case of upper bound, we can say that upper bound, so you can say the upper bound. So lower bound is nothing but minus 10.375, and upper bound is 62. That's mean after 62, all of the values considering as outlier, and lower bound is minus 10.375. That's been minus 3.75. Rest of them as nothing but as considering as outliers. Okay, so that you can see. So okay, you can see q3 minus q1 and q1 minus 1.5 into q1, and formula is good as well. So, and after that you can see you have the 39 outlier. That's when you have the 800 data, And if you're removing this 39, so rest of them consider as your data sets. Okay, so you can also do the same thing in the case of result. So you can copy this out, you can pass it to here, and in the case of age you can using the result. So result, and you can make it result, and the result, this is the result outlier. Okay, so result outlier like that. So you can printing it here, the upper bound, the lower bound. So in the case of result, upper bound is 23. After 23, considering this one as outlier. So after 23, you can see it's considering this one as outlier. And after minus 5 point something, it's considering as the outlier. Okay, less than minus 5.5. So you can also checking here this outlier, length of outlier. So you can checking here the result outlier. So outlier that you can see just have the one outlier. Okay, that you can see on here. You can see on here just one outlier. Okay, nothing fancy. Now what you can do, we simply going to checking here all of the columns and just have a look the count plot. Is there any imbalance inside our data set or not? And you already see that it have the data imbalance in the case of class AST. Okay, but what if I have some another imbalance in any kind of columns or categorical columns? So let's have a looking this out, and after that you're going to building here the machine learning model, and also going to replacing this outlier below with them. Okay, let's try to doing this out. So let's say df dot columns. So you have those columns. Now what I can do is simply creating here an list of that. So this is called the categorical columns. Categorical columns means because it just have the two values, that's why I'm considering as a categorical column. And also it having some kind of string type of data, so that's why. So what I can do, I'm going to copying here this one, the full one, and after that I'm going to be removing from here. So I can removing here the age, the result. So I can remove the result, as well as I can removing here this class and ASD. That's it. Okay, and all of them as considering as a category column because it just have the 2 or 3 values. Okay, so let's try to do one count plot. So we can using here for columns in categorical columns, and after that you can using here SNS dot count plot, and you can give it here x is equal to df of columns. Okay, and then you can give it here plt dot title. So let's say f, we can say that count plot. Okay, plot for the columns, and then you can using her x11. So you can give it to the column name, the same column name you can give it to as x level, and in the case of y level we can give it to here the count, and you can using here plt dot show. So you can see on here you don't have any imbalance. We can see that same thing on here, same thing on here, same thing on here. In the case of a5 it's quite imbalanced, but not so at all because it's 50-50. But in the case of s6, same thing, 50-50. So we can checking this out. Gender is also 50-50. So in the case of count plot for the ethnicity or ethnicity, what is called, uh, it also has some ruler below in the case of the others and everything. No problem, you actually replacing this out. And jaundice, autism also have the some uh, the imbalance problem as well. Okay, but the most one is imbalance in the case of used app before, and in the case of relations we need to replacing all the value from here. Okay, that's it, the count for from here. Now, so first you're going to replacing here this ethnicity. uh it's better you can also plotting here this our target class as well, so that you can add it to the your peppers. So let's say xldf of class asd, and you can give it to here title. Let's say plt dot title count plot for class ASD, and then we can give it here the X level. So make it class ASD, and you can using here Y labels. So you can give it to the count, and then you can using here plt.show. Now you can see it totally have the imbalance data set of data set, right? Cool. थोड़ा पानी पी लिया, sorry for that actually. इतना टाइम से बग बग कर रहा हो ना तो. So now we can check the value counts. Let's say df of class ASD dot value counts. You already checking this out, I hope so. Yep, you're already checking this out. Now let's start replacing here this one, the ethnicity, this one. So we can using this one. Okay, let's start to copying this out, or you can simply do copying this out, and you can simply paste into here so that you can clarify this one, okay, correctly. So copying this out, and first you can replacing this one. Let's say ethnicity, and then we're going to using this one. We can replace it. So replace it. So the question mark should be the others, and then the small others should be also the others, because this is the case sensitive. Okay, that's it. Now we can replacing it here the another one. So but tagging this one, is it correctly replace or not? Okay, unique. Yep, others: white, European, Middle Eastern, Pacifica, Black, Hispanic, Asian, Turkish, South Indian. Okay, let it. Cool, it will replacing them. Now let's start checking it here in the case of relation. So relation unique. So self, relative, and also have the this question mark. So you need to also replace that. So let's say relation, and you can using here the same thing. Df of relation dot replace, and you can replace it. So we can replacing here this question mark to the others. There's others, and you also replace here the relative, the parents, and the health professional, because it's not needed at all. Autism is depend on the self cases, so it's better you can make it as just in the case of self. Okay, so we can simply go into the relative. I mean, just making all of the case the parent relatives should be the others. So it should be the others. I mean, we just have the two column. I mean, two values in the columns, and then we can give it to the parents. Others, so that you don't do the hesitations. We can just getting here the two value on that. So it will be better for me. So you have to do the label encoders. So this one, and then making here these others. Okay, relatives, parents, and the health professional should be the others. Now you can simply go to checking this out. Relation dot unique. Now you can see that it have the self and the others. Okay, why actually making this parents relative healthcare professional to the others? Because I just make it as a two classes. It will be better for me to do the label encoder. That's why. Now you can simply go into checking here the object data column. So let's say object columns. Let's say object column. I mean, who are nothing but the string column or the categorical column itself. So we can using here df dot select dtype, and you can include here the object, let's say object, and you can using here the columns. So we can using here include, we can include here the objects. So you can copy this out, and then you can simply using here this columns. Okay, anything else wrong? Select the type, it should be the type. So the object column, it have, so gender, ethnicity, jaundice, autism, country of RES used before relation is nothing but the object column or the string column. So what I can do, you can be converting them into the categoricals, so the numericals. So we can simply going to take it, let's say for column in object column, and then we can using here this level encoder, let's say level encoder. And now let's getting here instance of that, let's say label encoder, and then you can use it in the case of column. Df dot column is equal to label encoder dot fit transform, and you can pass it to here the column name itself, and to also store it inside one encoder so that you can also see it. So let's getting here dictionary, let's say encoders. So let's say encoders of the column name, and then you can using here this level encoder, and then you can store it. Let's open. If you're not getting here any application, you can also using here this encoder. Okay, encoders.pkl. Okay, in some kind of cases you actually develop it in the web, so you can using here this encoder, you don't need to do it again and again. Okay, so let's say pkl.dump and encoder f. Okay, so it is saved. You can see encoder.pkl file that you can see on here. Now what I can do is simply going to checking here this encoders. So you can see here it will apply here this label encoder. So you can also use here the ordinary encoder if you have the multiple types of classes, but because in the case of me, it just have the two classes as well. Okay, you can also use it here in a kind of encoder technique. Okay, now we can checking here the correlation matrix so that you can see that we need to removing any feature or not. So you can using here an heat map. So I'll pause the video because electricity is gone. So when electricity is come, I will back again. So now let's get here the correlation matrix using sns.heatmap. So we can add here one figure size, let's say figure, and you can simply going to give it here a fig size. Let's give it to here 15, 15. And after that, you're going to using here sns.heatmap. And inside that, you're going to passing here df.core. And then you can give it here the annote should be the true, so that it will give you the annotations. And cmap is nothing but a color map. So let's say give it here cool worm, and you can give it here the fmt. So you can give it here 0.2f, and after that you can give it here a title. So let's say correlation. Okay, should be correlation heatmap, and then you can show it. Let's say plt dot show. Then you can see one correlation heat map that you can see on here. Okay, so you can see some of the value is highly correlated and some of the value is also negative correlated. Okay, but most of the value you can see is not greater than zero point 0.5. If I see 4.5 0.51 to this value to this at 3 score to the at 6 score, But if I see the most of the value is not highly correlated, if it is highly correlated, it will try to give it here one red kind of colors. Okay, red kind of color if it go up to 0.8, and you can see that you don't have any uh, this much red color. That means it's not a highly correlated. So if the column is highly correlated, then you can select in some feature and you can drop some feature from here. So I don't need to do any feature engineering here, so you can directly go to the next move. So next what I can do, we already creating here the functions for the IQ, right? If I see that we're creating here these interquartile arrays, I mean we actually taking the outlier, but we are not yet use it in our data frame. Okay, so what I can do, we can simply go into use it and apply it to our whole data frame. So that's why I'm going to creating here a function called replace outlier with median. Okay, let's say with median, and we can simply going to give it here df dot column, because if I see that we actually apply it to the data, but um, we are not actually replace it, because you can see that uh, if I see on here, you can see actually using it here, uh, the result outlier and the age outlier, it will actually remove it from the data set, but we are not replace anything in the case of these values, because we have the lower number of data. So what we can do, we can replace it to the median, because this is nothing but an categorical types of data as well. So you can see we're taking this out, and then we can using here the same formula that you actually use it in here. So if I go, you can see the same formula that I can use it, and I can simply going to pass it to here. Okay, so pass it to here just to do some indentations, and then inside this result we are going to give it to the column which is coming, and same thing for here column. We have the lower bound, we have the upper bound. Now we can take in the median of that. So what I can do, you're going to creating here a function, sorry, variable called median, and you can take it from the column, and then you can simply go to using here this median, and then you can simply replace it. So let's replace it. We're going to use it here. Now let's say df of column, and you can replace it, and you can apply here, apply here the lambda functions. So let's say lambda x, and you can using here the median. So if the x is less than lower bound, or the x is greater than upper bound, so those value is nothing but the less than lower bound. Okay, it will replacing this the median value of that. Same thing for the upper cases. That's why actually I added here the else cases, sorry, or cases. Otherwise you're going to replacing here with the same values. Okay, and then you can returning here our data frame. Okay, return the df. Now if I see the df dot head or df dot shape, so we have the 820 is nothing but our columns. So now what I can do, we're simply going to replace it. So let's say replace, okay, sorry, okay, let's say replace, okay, raw and convert, it should be the code. So replace with outlier, replace outlier with median, outlier with median, and we can simply go into passing here our data, and you can give it here the age and the result. So this is the inside the same data frame, because it's returning here the same thing. So we can pass it to here, and this is nothing but the result. Okay, now we can shift enter. Now we can check the data set. So this is how the data set look like, and if I see the shape of that, so you can see the same shape, but it is replacing with the median value. Okay, because if I see on here, yep, it will removing that, it will collecting the data, it will just replace in the same value, but it not removing the data from here. Okay, so those are the outlier that is found on here but not removed here. Okay, now we replacing this outlier below to the median. Now what I can do, we can simply now divide our data set into dependent and independent features. So let's say x is equal to df dot drop. So we can dropping the class and sd and accept them, all of the value is going inside this x. And then we have the y. So y is nothing but df uh, plus sd. So we divide our data set into dependent and independent features, right? Now you can simply go into pass it to the train, test, and split. So let's say train, test, and split, and you're going to passing here the x comma y, and you can give it here the test size should be the 0.2, and you can give it here the random state is equal to 42, and it could be the x train, x test, y train, y test. So now if I see the shape of this x train dot shape, so you can see the shape of the x train. You can also checking the shape of the y train as well. So this is the shape of the y train. You can also checking the below count for the y train as well. So let's say y train dot below counts. So you can see that it just having the 515 is nothing but a zeros and 125 is 1. That's mean this is an unbalanced data set. So what you can do, we can actually using here two technique. So either you can removing the 125 value from here, or sorry, not like that. Either you can making this 0 to the 125, either we can making this 1 to 5 into the 515. Okay, that's mean we can do the undersampling or the oversampling. So if I do the undersampling, our data is decreases. So if I do the oversampling, our data is increases. That's also one problems. Actually, what happening here, it will be adding here some kind of noisy data as well. But we don't have any another way to do that. So that's why you can using here the oversampling, because we have the limited number of data. So if I have the burst number of data, we can directly removing it from here. But it's not a good practice to remove the data. So we can simply go into creating here an instance of the SMOTE, because we actually using SMOTE in case of oversampling. So we can edit here the random state, let's say 42, and creating here a instance called SMOTE, and we can using here SMOTE.fit, and we can simply go into using a fit resample, and inside that you can give it here my X train data and the Y train data. Okay, because this is the actual data at all, not in the testing data. So the testing data shape, we having the same things, so you don't need to do it because it is nothing but the testing. But you're going to use this oversampling or the undersampling in the case of training data. So you can using it here. Let's say x train underscore smooth, and we can using here y train smooth. So using this data set, we're going to training our models. So let's shift enter. Now you can checking the shape of that. So you can see y train smooth should be. So you can see right now 105 1030. That's been 515 into, sorry, not into 515 at or plus 515 is nothing but 1030. That's mean you're doing the oversampling. Cool. Now we can simply going to apply it to the machine learning models. So what I can do, we're going to creating here an dictionary for the models, and after that you can use it and you can do the hyperparameter tuning. So let's creating here an dictionary. So first we have the decision tree classifier. So we can say that decision tree classifier, and then you have the random forest classifier, and then we have the XGBoost classifier. So let's say XGB boost classifier. So in here you can give it here some random state. So let's say random state, let's say 42, and you can copy it and you can paste it here in every of the machine learning models. And then you can copy this one, paste it, and you can copy this out, we can paste it, we can copy this out, we can paste it with the name and the algorithms. So this is the models. Now we can simply taking here the models from using here in for loops. So let's say for in models dot item items. Okay, so this iterator, it will give me two values. One is the model name in string format, another one is the model itself. Now we can simply going to add here some printing statement. So let's add it here f string. Let's say training, give it here the model name with default parameter. Okay, default parameters, because you're not doing any hyperparameter tuning yet. Later on you do it. Let's have a look first with the default parameters, and then we are going to add it here, calculate the scores. So we can using here the cross validation score, we can give it to here the model, the x train of SMOTE and y train of SMOTE, and you can give it the cross validation fold should be the 5, and scoring should be the accuracy. Okay, and then we can store it inside a dictionary. So we can creating here an empty dictionary for that. Let's say cb underscore scores. Okay, and here you go, we can add it. Let's cb underscore scores, and you can give it to here the model underscore name is equal to scores, and then we can printing this out. Let's the print f, we can give it to here the model name, and this is the cross validation accuracy, and you can simply using here is np dot mean, and you can using here the scores, and then you can give it here the point to f like that. Okay, and now we can printing here one berry cat. So let's add it to here berry cat. Now let's see anything error. So the scoring parameter checking must be in string. Okay, it should be string. Scoring, it should be give it here inside the double accuracy. Now you can see here in the case of decision tree, you got in here 86% accuracy. In the case of random forest, we got 92, and in the case of XGBoost classifier, we actually getting here the 90 as the value. Now if we're checking here the cb scores, cb underscore score. So in the case of decision tree after 5-fold, you can see that we got 87. If I just taking all of them and if I divide them with 5, so if I summing this all of them, so let's say I'm going to sum all of them and sum all of them just for ensure that how it actually calculated. Okay, then we can divide it to the 5. So divide to the 5, we can simply going to give it to here same bracket. So we got here 0.856. That's mean you can make it as a 86%. Okay, that you can see on here. Same thing for the random forest and same thing for the XV classifier. Okay, this is how it actually calculated. Now we're simply going to initialize the model, and after that you're going to do the hyperparameter tuning. So let's try to using here this decision tree classifier first. Decision tree classifier with the random state of 42. Then you have the random forest classifier with the random state of 42, and then you have the XGB classifier, the random state of 42, and just give it here some name. Let's say decision tree, and we have the random forest. Let's say random forest, and you have the exiboost classifier. Let's say exiboost underscore classifier. Just initialize this one so that you can also do the hyperparameter team, right? So for that, you're creating here some param grids. So let's say param grid for decision tree. So we can give it here the criterion. So let's say criterion. So in the case of decision tree, it have the Gini and the entropy. Okay. If you don't know what is the Gini entropy, you can just go and watch the videos about the decision tree from scratch. Okay, then you have the max depth. So max depth, let's start from none, and let's say 10, 20, 30, 50, 70. You can selecting here any kind of value from here. Okay, and then to give it here comma as well, we have the mean sample split, mean sample split. So we can give it to here. It's a 2 comma 5 comma 10, and then we can give it here the mean sample leaf. Okay, split and a leaf. Okay, 1 comma 2 comma 4. Now we can do it for the random forest. So let's pass it to here. This should be the RF, but in the case of random forest, it having some changes. So in the case of entropy, we can give it the number of estimators, because it's by default using here the decision tree classifier. So let's say 50, 100, 200, 500. Okay, there you then max depth, mean sample split, and the mean sample leaves. So you can decrease this out, because we don't need to do the any depth yet, because otherwise taking time, because it's internally using the decision tree. So mean sample leaf, like that's fine. And then it also give it here one bootstrap. It's called the bootstrapping. Okay, it will bootstrapping all the value. It will giving here the actual result. So true or false. Okay, now you can do the same thing for the XGB classifier. So you can copy this out. We can make it as XGB. Now in the case of XGB, so all other things are same, just not adding here one learning rate. So let's say learning rate, and let's give it here learning, let's say 0 0.01, 0 0.1, 0 0.2, and 0 0.3. And we don't have any mean sample split or mean sample leaf. It's just having an subsample. So we can using here the sub underscore sample. So we can make it as a 0 0.5, 0 0.7, and 1.0. Then you have the call sample by tree in the case of XGB. So I actually not creating the very uh, video regarding this XGB, but soon I will creating this one from scratch. But I creating the video about the decision tree and the random forest. Okay, because it is taking really time. Okay, so max depth you can give it to here 3, 5, 7, 10, because I don't need to give it here that much value, because this is an ensemble technique as well. So learning rate, and this one, and call sample by tree, you need to give it here some value. Let's give it here 0 0.5, 0 0.7, and 1.0. Okay, so anything wrong? I forgot to give it here on comma. So okay, it should be the comma as well. Okay, now we have our hyperparameter tuning. Now we can using here this randomized CB. randomized search cb, and inside that you can give it here the estimator. So estimator, you can give it the decision tree, and inside the param distribution you actually give it here the param in the case of dt, and number of iterations, let's give it here 20, and cross validation score, let's give it here 5, and a scoring, let's give it here accuracy, and then give it here the random state. So random state you can give it here 42. Okay, so you can copy this out. Okay, first we are going to making here a variable, so we can make a variable call, let's say random search dt, that's a random search dt, because this is nothing but for the decision tree. And after that we are going to using here for the rf, so it should be the param greet rf, param greet xzb, and all of the values are same, just due to changing here the estimator. So random forest, and we have the xzb boast classifier, it should be xzb boast classifier. And also here you go, you need to give it here the variable name. So instead of dt you can using here the rf, and in here you can give it here the xzb, that's it. Okay, now we have the classifier as well as we have everything. Okay, now you can simply go into feed it to the model. So you can using here this random forest dt, then you can using here the random forest rf, then you can using here random forest xzb. So you can using here dot feed, you can using here xtrain SMOTE and the y train SMOTE. So you can copy it, we can paste it to here, right? So it will taking a few times, and it will, because it will using here this iterations of the 20. So now what I can do, we can simply go into using here some if and else condition here to getting here the best value from here. So what I can do, we can creating here an variable called best model. I just make it as a nan, because from the 3 model 1 should be the best, and also the making the best score should be the 0. And then you're going to creating here some if and else block. So here you can give it here some kind of conditions, and you can store the value inside the best score and the best model. So if the random starts, you can see it will start it will subsample are not used. Okay, so if I see the subsample, okay, it not sub underscore sample, it should be a subsample just. Okay, so I need to stopping this out. Okay, it is stopping this out because the it's not a subsample underscore sample, it should be subsample just. Okay, no problem, we'll run it later on. Let's run it here, right? Because it will running it for the 60 time. You can see 30, 32, 32. Okay, 16 time. You can say random search cb. Okay, so you can say random search cb, it have the xzb classifier. Okay, now it will execute it, but in case of here I need to also running it again because subsample is not used, so I need to use it right now. So let's use it now. We can using here the same thing because it don't have any subsample like that. Okay, now we can simply go into creating here some kind of if and else block. So let's say we can say that random search, we can say that dt, so let's say search dt, and if it is dt dot best score, best scores score, so it is greater than the best score that I created. It will working, yeah, that's what for that. So if the random search dt dot best underscore score underscore if it's greater than the zeros, then we can simply go into making the best model to the this one. So let's say best model is equal to random search dt dot best estimator. So we can using here best st matter. Okay, st matter underscore, and then we can also calculating here the best score is equal to random search dt dot best score. So we can say that best score, so score this one. So this is for the tt. Now to do the same thing for the rf and the xgb. So let's go on here and go on here. So let's make it as a rf, and this is for the rf, this is for the rf. Same thing for the xgb, so xgb, and same thing for the xgb, and same thing for the xgb. Okay, that's it. Now you can shift enter. Now you can searching for the best model. So you can checking for the best model, and our random forest classifier is the best model. We can also checking here the best score. So let's say best score. So best score is 0.92. Okay, after the uh, randomized search cb. You can also use the grid search cb as well. Then after that we can checking for the cross validation score as well. Cross validation score is nothing but you can calculate them. Okay, now you can saving this out. Let's say with open, we can say that best model dot pickle. We can save it as f, and you can using a pickle dot dump best model, and you can using the f. So it will save it here. You can say best model dot pickle file. Now you can using this one into creating here the Flux applications. But in this video, I am not going to creating this out because it's already taking more amount of time. So it's your job to creating this out. Okay. Because I'm already making so many videos regarding this one, so you can easily do one practice system and you can easily testing this out. So you can also testing it out. Let's say predictions is equal to best model dot predict. We can predict it in the case of x test below, and based on that you can calculate the accuracy, confusion matrix, and the classification report. So let's say accuracy score. We can give it to here the y test and y test pret. So accuracy score in the case of testing data is nothing but the 81%. And if I see the confusion matrix, you can see this is the confusion matrix. Okay, and also you can checking for the classification report that you can see. So you can painting this out, then it will look good. Okay, here we go. So you can see precision, recall, F1 scores, and the support. Okay, so this is how this autism spectrum disorder is work, and you can using here this model to creating here and applications. So that is what today now. Hope you enjoy this full tutorial, and make sure to subscribe to the channels and share with your friends.